Hey YC, my name is Joe, and one of the most technical projects I've built is OralScan, a mobile-based oral cancer diagnosis system that runs on a novel computer vision pipeline I spent a year researching and developing. Before I dive into the research behind OralScan, I want to show you a quick demo.
This is the OralScan app. After signing in with Google, users first see their previous diagnoses. By selecting a specific diagnosis, they can access more detailed information. On this page, users can find nearby screening locations and get directions with a single click. Additionally, they have access to a curated catalog of reliable resources for oral health information. To make a new diagnosis, patients simply take an image of the mouth, fill out the 5-question survey, and in under 15 seconds, they can see a detailed diagnosis regarding lesion location, type, severity, and future directions, getting a full oral cancer screening from the comfort of their home. So before we dive into the code base, here's a quick overview of how the models work. The 4-block architecture uses 2 pre-processing blocks that eliminate noise and 2 multimodal blocks that classify the type and stage of a lesion, creating a funnel-like pipeline that reduces noisy features at each step. To train OralScan, I collaborated with several universities to compile a dataset of over 6,000 images. A challenge I ran into early on was that many of the datasets only annotated with bounding boxes rather than the segmentation masks. To address this, I created several data standardization algorithms to generate size-relative segmentation masks for every image. Here's the integration I created for RoboFlow datasets specifically. This pipeline crops each bounding box and then applies a custom adaptive contour detection algorithm to produce a mask. Specifically, in this process, the L channel of each cropped ROI is Klein normalized and bilaterally filtered. Then, it's segmented via a fused Otsu plus adaptive Gaussian threshold before being morphologically opened and closed, and then being passed through the fine contours algorithm, which simplifies the winning contour into a YOLO seg polygon, maximizing area while minimizing the size. On the architecture side of things, OralScan uses a first-of-its-kind multi-stage pipeline for pre-processing raw intraoral images. The initial model segments the oral cavity, then another model segments the suspicious lesions. This two-step approach improves accuracy by nearly 20%. For each unit, I ran experiments across different backbone architectures, model depths, and both model and training hyperparameters, capturing detailed performance metrics using this function. To sweep the full hyperparameter space efficiently, I built an asynchronous orchestration layer that fans each configuration out to isolated Docker containers, streaming every run's metric into a unified CSV file for downstream analysis. To ensure that the units would not overfit, I also created a data distributor that ensures that the total ratio of non-mask pixels to mask pixels remains consistent across the training, testing, and validation pools for both segmentation models. The result? An oral cavity segmentation model running at 97% accuracy, and a cancerous lesion segmentation model running at 94%. Both of these models outperformed every industry benchmark, including both state-of-the-art AI models and doctor-facilitated intraoral inspections. As you can see on this result board, here's the performance breakdown for oral cavity models, and here are the results for the abnormal lesion classification model. The final stage of this architecture handles classification. The first multimodal classifier extracts a feature vector from the lesion image using a decapitated and fine-tuned Inception v3 model. Then it combines it with a feature vector that is derived from a list of patient risk factors such as their age, tobacco usage, and drinking habits. Both of these vectors are fed into a fully connected classifier to determine whether the lesion is cancerous or benign. If cancerous, the lesion is passed to a second fine-tuned Inception v3 model that distinguishes the cancer between early and late stage. Unfortunately, I can't show you the training code behind this process since all of it lives on UARK servers. However, I can walk you through some of the interesting data preparation works. One specific technique I used was compartmentalization. I split each class into 2 modalities based on lesion morphology. Small lesions, which tend to appear as distributed patches, versus large lesions, which formed a single continuous mass. I used contour analysis in basic linear algebra to measure lesion type, and then applied a histogram in order to identify the national threshold before these 2 types of lesions. Each model was then trained separately on small and large lesions before the weights were combined, creating a classification model that was both reliable and accurate. This was the technical work that I put behind OralScan, and it was so meaningful to me because it solved a problem that I saw growing up in rural India. And I hope through the YC Fellowship, I can create more technology that bridges the gap between the medical care that every human deserves and the financial and resource burden that stands between them. Thank you so much, and I hope to see you at SF.